get started. Okay, so welcome everybody. Hope everybody's doing fine today. I just started the recording, so if you want to type your name into the chat now for attendance, if you type it in now, it will get recorded. So I'll write, you're not getting me. Are other people getting me? I got a message that Theophilus is not. Are you getting me? Is it okay?
Yes.
People are getting me. Okay, so Theophilus, it's probably on your end. You need to check your volume. So I'm just gonna write, please. Hello, hi Abraham. Type your name into the chat for attendance. Okay, so sorry, I'm gonna let me okay, Harrison, is it okay? Okay. Everybody. Okay, so yeah, so welcome everybody. You can type your name into the chat at any time. For attendance. Just make sure you put your name in by the time I turn off the recording. Okay, so I hope everybody's doing well. I know we had a week off, but we talked about regular polygons last week, and we're going to spend a little bit of time talking about circles today. And maybe before we do that, let me just announce I only sent out a schedule for the fall semester, and we're basically getting into the spring semester. So we're going to choose a new topic for the spring semester starting in maybe 2 weeks, at which point I'll send out a schedule of dates for the spring. But we have a few choices, so I'll send out a message about this. But the choices are, we could either just do more geometry and do it more seriously, do some proofs and things like that, or we could pick another topic. So I'm gonna open it up for your input as to what topic we do starting in February, because we'll probably finish up this current geometry unit in January, finishing up what we're going to say about circles, and then in February we can start something new. So I'll accept some input for that. Okay. Maybe, I guess, 3 more sessions on geometry before we start a new unit. Okay, so all right, so welcome everybody. And if you recall, last time we talked about these regular polygons, and we had a couple of homework exercises. So the first one was, suppose that a regular hexagon has side length s, and the question was, what is its area? And the next one was, compare your answer above to the area of an equilateral triangle with side length s. And the question is, how many times bigger is the hexagon's area? And can you give a geometric reason why this should be true? And just to recall, because it's not an easy formula to remember, I mean, it's not a formula that I remember, we have to look this up, is that we have this formula for the area of a regular polygon with n sides of length s, right? So the area is equal to n times s squared divided by 4 times the tangent of 180 degrees over n. Okay, this is a formula that we derived last time in the notes, so you can see that derivation that we have here. So to answer the homework questions, we can plug in the number of sides to the formula in order to get that. So let me just recall this here. Recall just area equals ns squared divided by 4 times the tangent of 180 degrees over n. Okay, so this is just recalling this formula. And so for question number 1, right, we have a hexagon. So for question number 1, we have that n equals 6. And s is just s. I haven't told you what the side length is. We'll just leave it as s, right? So in this case, what do we have? We have 6 times s squared divided by 4 times the tangent of 180 degrees over 6, which is equal to 6 times s squared divided by 4 times the tangent of 30 degrees. And people remember, what's the tangent of 30 degrees? Mm-hmm. Exactly, thanks. Right, so root 3 over 3, exactly. So this is 6x squared divided by 4 times root 3 over 3. And if we want to make this into a simple fraction, this is 6s squared over 4 times 3 over root 3. And for now, so we'll call that 18s squared divided by 4 root 3. And I'll cancel out a factor of 2. So that's 9s squared divided by 2 root 3. Okay. And so maybe I'll just leave this for now. I'm gonna leave this as is. Okay. So we'll call this the answer. We could rationalize the denominator if we want to, but I don't really see much of a reason to do that. I'm happy leaving square root of 3 in the denominator. Okay, I don't need to
Yeah,
rationalize
Andrew.
it. Yes, Clinton?
Yeah. So we can we write 9 as 3 times 3, and then root 3 goes into 3. It becomes 3 s squared over 2.
Yeah. So we could do that. So okay, if we want to do that, we can certainly rationalize this. So this would be, 9 is going to be 3 times 3s squared over 2 root 3. And then 3 divided by root 3 is root 3, right? So this would come to be 3 square root of 3s squared over 2. So if you like this form of the answer better, then that's perfectly fine. Yeah, they're both correct.
Okay, thanks.
Okay, you're welcome. Yeah, so you can rationalize the denominator if you want. You don't have to if you don't want to, although it's good for students to be able to do that, because if they're given a multiple choice question, the answer might be in one of the two forms, and they may need to convert one form to the other form, right? Okay, so for a hexagon, this is pretty standard, and it's just a question of plugging in n equals 6 to the formula. Okay? All right, so we get 3 square root of 3 s squared over 2. That's the area of a hexagon with side length s. Any questions on this? Okay, so number 2, we're asked to compare this to an equilateral triangle, right? So number 2, we have n equals 3, right? And in this case, we did this last time. Actually, we did this last time, and the answer came out to be s squared times the square root of 3 divided by 4. Okay? Right? So the question asks, so this is just what we did last time, or you could also do this by plugging in n equals 3 if you want. You get 3s squared divided by 4 tangent of 60 degrees. And if tangent of 60 degrees is square root of 3, and if you simplify everything, then this is what it comes out to. Okay, so this is the result that we got last time. And now the question is asking, how many times bigger is the hexagon's area? So we have to take a ratio, right? So ratio, if we take the hexagon area and we divide it by the triangle area, well, what is this? This is, I guess, okay, I'll use Clinton's form. So 3 square root of 3 s squared over 2 divided by, that's the hexagon area, and then divided by s squared square root of 3 over 4. And we can make some cancellations here. Well, the s squareds disappear, and the square root of 3's disappear. And so we have 3 halves. So this becomes 3 halves divided by 1/4, which is the same thing as 3 halves times 4, which is the same thing as 12 halves, which is 6. Okay, so what that tells us is that the hexagon area is 6 times the triangle area. Okay, so the hexagon area here, which we got as 3 square root of 3 s squared over 2, is 6 times the triangle area, which was just s squared square root of 3 over 4. Okay, so we just have the two formulas, we take their ratio, and that tells you how many times bigger the hexagon is than the equilateral triangle. So that's fine. We can plug in the formulas and get an answer, and we have that the hexagon is 6 times as big. But the second part of the question says, is there a geometric reason why this should be true? Let's say you didn't know this formula. If I just asked you, how does the area of a regular hexagon with side length s compare to the area of a regular equilateral triangle with side length s? Is there any way that you could just know that it's going to be 6 times as big, even without knowing this formula? Any ideas? Okay, well, let me draw a picture. Okay, so I'm going to draw the following picture. Here is a regular hexagon with side length s. So S, 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 S. And now I'm going to divide this hexagon up into 6 equilateral triangles that all have side length s. Right? This is 6 triangles because remember that the angles in a hexagon, the interior angles in a hexagon, if you recall what the interior angles are, well, we don't even need to know this, that they're equal to 120 degrees. But even if you didn't know that, you know that if you make this division, every single one of these angles, you've divided the full circle up into 6 parts. So every single one of these parts is going to be 60 degrees. And then since these triangles are isosceles, we know that the other 2 angles have to be equal. So all of these angles are also 60 degrees. And so on. I'm not going to label every angle because it's going to make the diagram too cluttered. But what we have is that the hexagon is made out of 6 copies of the equilateral triangle. Okay, so this explains exactly why the area of the hexagon is 6 times as big as the area of the equilateral triangle, right? Because the hexagon is just made out of 6 copies of the equilateral triangle. Okay, so you add up the 6 equilateral triangles and then you get the hexagon. And this is an equilateral triangle with side length s, and this is the hexagon with side length s. So you end up getting this exact ratio of 6 to 1 for the areas. But this also comes from just applying the formula. You get a ratio of 6 to 1. But this geometric reasoning is nice because you don't need to know the formula in order to figure out the ratio. Okay, any questions on any parts of these exercises? Okay, if there's no questions, we'll move on then. All right, so it's the area of a regular polygon. We can skip that. Okay, so today we're going to talk about circles. And since we're introducing circles today, we're going to basically just do basic things about circles. And next week, we'll cover some more advanced topics involving circles. Okay, so for today, we should start always with a definition. So basics of a circle is that a circle is the set of points in the plane at a given distance from a fixed point. And that fixed point is called the center. So everybody knows what a circle is. We have our center, and we take all of the points that are a certain distance from that point. So every point on the circle is the same distance from the center. And the distance from the center to any point on the circle, this is called the radius, which we usually call r. And if we have a line segment from one point on the circle to another that passes through the center, then that's called a diameter, right? So if I take one point on the circle and I go through the center and I go to another point on the circle, that's generally called a diameter, d. And the diameter is, of course, just equal to 2 times the radius. right? And then when we talk about the perimeter of the circle, which is the length of how long it is to go around the circle, we have a special word for it, which we call the circumference. Okay, I mean, it just means the perimeter. And physically, what does this mean? Physically, this means that we're trying to, what is the length? It means if you had a string that was formed into a circle and then you pulled the string apart, how long would it be? Actually, in mathematics, to define length is not so trivial. When you're talking about length of a curve as opposed to a straight line, you kind of have to use calculus to define what the length is. You really have to use an arc length integral. There's no other way to define the length. But we will just use our standard, basic idea of what length is, which means that you unroll it and you see how long it is, and that's the circumference of a circle. Okay. So these are the most fundamental quantities that are associated with a circle. Okay. And so there are some formulas for circles that you probably mostly know, but it's worth going over it. So first, if a circle has radius equal to r, then the circumference is given by this formula 2 pi r, or in other words, pi d, pi times the diameter. And somehow I wouldn't really say that this is a formula that you prove. What this basically is you should think of this as the definition of pi, right? So I mean, what's pi? You say it's 3.14159, blah, 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 blah. But what is it really? And the answer is that if you draw a circle, pi is the ratio of the circumference to 2 times the radius, right? I mean, we have our formula, circumference equals 2 pi r. This is the same thing as saying that pi is equal to the circumference divided by 2r, right? And what this formula is saying is that no matter what your circle is, if you take this ratio c divided by 2r, you're going to get a constant, and you're always going to get the same constant no matter what your circle is. Okay, and that constant is pi. Okay, so you're always going to get the same constant no matter what the circle is. Okay, so in some sense, that's the definition of pi. It's saying that people observe that if no matter what you do to a circle, if you stretch it, if you compress it, the ratio of the circumference to 2 times the radius, or the circumference to the diameter, is always the same. And that is the number that we call pi, whatever that ratio is. Okay. So now we have an area formula for the circle. And the area formula for the circle is fundamentally different than all of the other area formulas we've done so far, right? What area formulas have we talked about? We've talked about the area of a square or a rectangle, and then we did triangles and we did parallelograms, and we justified those by showing that a square was made up of 2 triangles, and maybe a parallelogram was made of a rectangle and 2 triangles, and we added up all these areas to get a justification for these area formulas. And then we even did regular polygons, like in the first part today. We talked about, the area of a hexagon, and in general, the area of an n-sided regular polygon. And we did that by dividing everything up into triangles and using the triangle area formulas and then adding them together. So a circle is somehow very fundamentally different than all of these polygons we've been working with, because a circle doesn't have straight sides, right? A circle is curved. So everybody knows, or at least, most people know this formula for the area of a circle. The area of a circle with radius r is given by pi r squared. But it's hard to just give a real justification for that. And in fact, to really prove this, you need to use calculus. There's no other way to do this other than using calculus. But I can give you a bit of a picture justification as follows. Okay, so why should the area of a circle with radius r be pi r squared? Right, that's just not at all clear. Right, it's not like the area of a square, which is definitely s squared. Why does this pi show up? I understand why pi shows up for the circumference. Why does it show up for the area also? I don't know why should the area of a circle with radius r be pi r squared? So let me draw you this picture that will maybe help you understand. So let me draw a circle. I attempted a circle, and I'm going to draw the center. And what I'm going to do is I'm going to draw lots of different little wedges in the circle, equally spaced. I don't know how many, but a lot of them. Okay, so I'm dividing the circle into a lot of these little pieces. And, each piece is very close to a triangle. Right? Now, of course, it's not exactly a triangle, right? Because this circle is curved. So for each of these pieces, it has two straight sides, but the third side is not really straight. It's a circle, so it's got like a little bit of a curve in it. So it's not exactly a triangle, but it's pretty close to a triangle. Okay? So let me show you a picture of how you can like cut these triangles up and piece them back together. So if I do, so look at the following picture here. Can everybody see this picture?
Yeah, I can see it.
Okay, good. So here's our circle. It's divided up into all of these pieces, and some of them are colored blue and some of them are colored yellow. So what happens is if you take these pieces and form them like this instead, kind of the blue ones upside down and then the yellow ones, and you alternate, then you have something that looks like a parallelogram. And in fact, if you make the pieces really small, it starts to look like a rectangle. And so what are the sides of this? Well, we know that the circumference of the circle is 2 pi r, right? This is our formula for the circumference. It's 2 pi r. Well, what do we have? This top side is basically the yellow part of the circumference. The bottom side is the blue part of the circumference, right? And we see that each of those takes up half of the circumference. So the yellow part of the circumference is just pi r, and the blue part of the circumference is also pi r, right? So we have pi r down here for the blue part, and pi r up here for the yellow part. And what's the height of this parallelogram, or that's almost a rectangle? If you made the slices really, really small, it would start to look like a rectangle. Well, its height is exactly just this length over here, which is r. So what you see is if you cut the circle into lots of really small pieces and put them together like this, then what you get is almost a rectangle where the base has length pi r and the height is r. And so we know what's the area of a rectangle. It's base times height. So you end up getting pi r times r, and that's equal to pi r squared. And this is the idea, is that this is what the area of a circle is, right? This is a bit of an approximation. It's not exactly right because you've got some curves here on the sides, and this is also not perfectly straight up and down. But if you really use lots and lots and lots of little pieces, this here is divided into like 16 pieces, but if you divided it into 100 pieces, it's going to really look almost exactly like this rectangle. Pi r by r, which is going to give you pi r squared for the area. Okay? Now, how do you make this actually correct? Well, at some point, you have to use the concept of limit to take the limit as the number of pieces goes to infinity. And so this is an advertisement for calculus. One of the things that calculus does is it lets you actually make this into an airtight, rigorous proof that the area of the circle is actually pi r squared. Okay, because you can talk about the limit as the number of wedges goes to infinity. But even without that limit, you can still maybe believe from looking at this picture that you can basically chop the circle up into a lot of small pieces and you get a rectangle with side pi r on the bottom and r on here. And so the area is going to be pi r squared. Isaac, do you have a question? I see your hand raised. No? Okay, did anybody have a question about this picture or this derivation? So I like this justification, and there's no other way that I can really feel this area formula, this pi r squared. Like this is the only way I can really think about it. Okay. Okay, no questions? All right. So I'll take the picture away. Let me share this screen again. Got it. Screen. Yeah. And all right, good. Okay, so what you end up getting is I'll just write this down here, rearrange, and you end up getting basically a picture that looks like this. And this isn't going to be a particularly nice picture. And down here you have pi r, and up here you have r. But the better picture is this picture that I showed you from the internet. And maybe I'll give you the if you want to see the picture, you can follow this link here, and this is how you get to the picture. Okay. Good. Okay. So that's a justification for the area of a circle. So there's some other parts of circles that we ought to know about, some other vocabulary that deals with circles. So if I have a circle over here, if I take two different line segments that go from the center to the circle like this, then this area between them is called a sector of the circle. And if I take just any point, any line segment from one point in the circle to another point, then this thing here is called a chord. And if I look at the part of a circle on one side of a chord over here, this is called a segment. Okay, so the segment and a sector are two-dimensional regions, and a chord is just a one-dimensional line. So that's a segment. And if I look at just a part of a circle, a part of the circumference from one point to another, so a connected section of a circle here, this is called an arc. Okay, and so and an arc is measured in degrees, right? So we would have a full circle is equal to 360 degrees of arc. Okay, and then a semicircle would be half that, so that'd be 180 degrees, etc. So you can measure the arcs, and in fact, the arc length, if this measurement of this angle right here is theta, then the corresponding arc is also theta. So this corresponding arc over here is also theta. Okay, so the measure of an arc is the same as the measure of the central angle that cuts it off. When we say a central angle, we mean an angle made at the center of the circle. So that's going to be what's called the central angle. Okay. Any questions about this? Yeah, Clinton?
Yeah, Andrew, I want to ask a question regarding the previous slide. I thought you were asking questions about. I thought the question was about the figure you showed, but then can we define pi as meaning the ratio of the area to the radius square, just as we define pi in terms of the circumference as well?
Yeah, you can. It's just somehow a little less fundamental to do that, right? So you can, it's not wrong, but area is more complicated than circumference. So if you're going to define a fundamental constant like pi, you want to define it in the simplest way possible. So it's better to define it in terms of something one-dimensional instead of something two-dimensional. But it's not wrong. You could do it as the area divided by you could do it as the area divided by the radius squared. That'll give you the same definition. And in some
Okay,
sense,
so
the formulas working is saying that both definitions are the same. That's what it means for both formulas to work.
sure, sure. So for a cycle,
Mhm.
the for a cycle, the area is one dimensional, right?
Yeah.
Okay.
Yeah, so no, I mean, really, to define area, again, you have to talk about limits. I mean, you really can only define the area of rectangles, and everything else is defined by kind of how can you like put a bunch of small rectangles into it and approximate what the area should be. So, but we have an intuitive sense of area. You know, it's the amount of space that it covers, and if you could stretch the circle into a rectangle, then the area of that rectangle would be the same as the area of the circle. But really, I mean, to define area, I mean, and you know this because you know some integration, like you just have to, the definition of area is the integral. You can't do it any other way for
Yeah,
something that
sure.
has curves. Yeah. So, but I mean, for us, we have a sense that like basically area should be something that if you rearrange things and that shouldn't change the area. So if you can rearrange something into a rectangle, then its area should just be the same as the area of that rectangle. Okay. Other questions? All right. So, okay. So we have all of this other, circle vocabulary over here. And so just as an example of a kind of problem, so let's say that we have a circle of radius 6, and we want to know what's the area of the sector that's cut out by two radii that make a 60-degree angle, and the radius is 6. And then the corresponding segment, I'm just going to draw like this. Corresponding segment is going to be this area here in purple. Okay. So in this case, what do we have for the sector area? Well, we know that the whole circle has area, well, we have this thing pi r squared, and the radius in this case is 6, so it's pi times 6 squared, so it's going to be equal to 36 pi. So the sector area is equal to the circle area, but this sector is cut out by a central angle of 60 degrees, right? So the whole circle would be 360 degrees, but this sector is just 60 degrees. So to get the sector area, we have to multiply the circle area by 60 divided by 360. Right? This is going to be the sector, we could call it the sector proportion. Right? So in this case, what are we going to get? We get only 1/6 of the circle area, so we get 36 pi times 1 over 6, which is 30 over 360. Right, so let me just write that down. Right, so 60 goes to 1, 360 goes to 6. So we get 36 pi times 1 over 6, and this comes out to be 6 pi. Right, so 6 pi here is going to be the area of the sector. Any questions about this? Okay, and so what about the segment area?
So
Oops, question. Yep.
okay. I think to find the area of the segment, we can subtract the area of the triangle from the area of the sector.
Exactly. So sector area minus triangle area. Great. And so the sector area we already calculated, that's 6 pi. And how do we figure out the triangle area here? In fact, we have a formula for it.
So if I'm to find the area of that triangle, I will want to bisect the angle 60 degrees, and then find find out how to use the formula A is equal to 1 over 2 BH.
Right. So we can definitely do that, and that will work. But since since this is a very special triangle, we can do something a little easier. Right? So what kind of triangle is this?
Equilateral?
It's an equilateral triangle, right? And so that means we already have, if you go back to the beginning of the slides, we have the formula for the area of an equilateral triangle once we know what its sides are. So, I mean, of course, the way you derive this formula is by doing exactly what Clinton said. You have to draw a perpendicular and do 1/2 the base times the height. But since we have this formula, we may as well use it. So we know that the area of an equilateral triangle is s squared times square root of 3 divided by 4. Okay, so let's just plug that in. In our case, the side length is 6. So we have over here, the triangle area, right, is going to be, so it's 6 pi minus 6 squared times square root of 3 divided by 4, which is 6 pi minus 36 root 3 over 4, which is equal to 6 pi minus 9 square root of 3. And just as a check, you should check that this answer actually makes sense, right? Because in particular, you need to make sure that it's actually positive. So let me just check quickly. If I do 6 pi minus 9 times the square root of 3, yeah, this is about 3.26. So that's okay. So this is roughly 3.26. So that at least makes sense. You want to check that you're not getting a negative answer, because that wouldn't make any sense. Okay. So in this case, we were lucky, we had a nice sector. And so we have the two radii of the triangle, and in order to find the segment area, you can take the sector and subtract the area of the triangle. Okay. So any questions here? Okay. Just a reminder to everybody to type your name if you haven't done so yet. Yes, Theophilus? Is there a comment or a question? Yes, Theophilus?
Yeah. Yeah. I want to know the formula for radius, because I know the circumference to be 2 pi d, or sometimes 2 pi r. Right. So what will be the formula for radius? Can you please help?
And there's no formula for radius. The radius is usually just given to you in any problem. I mean, you can say that the radius is equal to 1/2 of the diameter, but I mean, beyond that, there's not really a formula for the radius. It's just the radius is usually just given to you, and it's part of defining the circle is that you say where the center is and you say what the radius is.
Okay.
Okay. Yeah. Usually, you're not going to have a formula for it.
Is it over?
Yes, Abraham?
So why in case you bisect this triangle and then find the height of the triangle to use the triangle area formula?
Yeah, you can do this. It just makes okay. If people want to do that, we can do it. I don't have a lot of space for it. Let me try to do it here. So yeah, I'm just going to redraw the triangle over here. So if we have 6, 6, and we bisect it over here, then we have 6 down here, and then you have to calculate the height. And in order to do that, you have to use trigonometry, right? So if you want to calculate the height here, you have to use the fact that this is 60 degrees, this angle. And then for the height, you could have that the height, using right triangle trigonometry, you could have that the height divided by 6. Sorry, you could have that the height divided by 6, right? If this is h, then height divided by 6 is going to be equal to sine of 60 degrees, because that's the opposite over the hypotenuse. And that's equal to square root of 3 over 2. And then you can solve for the height. So this gives 2h equals 6 root 3, or h equals 3 root 3. And so then, and I'm already running out of space here, but we could say that the area is equal to 1/2 times the base times the height. So 1/2 6 times 3 root 3, which comes out exactly to 9 square root of 3, which is what we got from this other method. So we get the same answer, which is nice to see. But just when we derive the formula for the area of a regular polygon, what we did was we basically did this. We basically divided it up into a bunch of triangles and then did this trigonometry process with the heights for all of them. So so it turns out that what you did here is basically equivalent to what you do when you derive the formula for the area of a regular polygon. And so since we have that formula, it's a little quicker to just plug in 6 for s here and get that 9 square root of 3 also. But if you want to do it by drawing a height and by using trigonometry, that's completely fine, and it's correct, and you'll get the same answer. But we have a quicker formula for the area of an equilateral triangle. It's just s squared root 3 over 4. Other questions?
Yes, sir.
Yes.
Yeah. Can you please confirm if I say, because even though it says radius is half of diameter, but what if I say radius equals circumference over 2 pi?
Yeah, I mean, that's fine also. If you're given the circumference and you want to solve for the radius, yeah, that works. Yeah, so you can have radius. Yeah, that's certainly fine. You can say the radius is the circumference divided by 2 pi. You could say the radius is the square root of the area over pi, right? I mean, you can always solve for the radius in any of these formulas. But usually the way these things are done is that you're given the radius and you need to find the other quantities. But you can also go from having these other quantities and then figure out the radius if you want to do that. Yeah.
Thank you.
That's fine. You're welcome.
Okay.
Other questions? So this slide unfortunately got a little bit cluttered, but that's okay. Okay, so want to talk a little bit for the rest of the day. We'll just talk a little bit about angles inside circles. So the most basic angle is what's called a central angle, which means it's formed by 2 radii. So you have one radius and another radius. And so I already mentioned this. What is the angle? If the angle is called theta, then the measure of the central angle is the same as the measure of the arc that it cuts out. So this is arc measure theta as well. Okay, so if the angle is 70 degrees, then the arc that it cuts out is 70 degrees. And if the arc that it cuts out is 70 degrees, that means the angle is also 70 degrees. Okay. Okay, so that's fine. Okay. So central angle is pretty basic. And to some extent, this is not even really a result. This is basically a definition of what arc measure is. Okay, it's saying if you have a central angle with a given measurement, then the arc that the word that people use is subtends. So the arc that the angle subtends, which means the arc that it cuts out, has, by definition, its measure is the same as the measure of the angle. Okay. Any questions? So central angle is the most basic angle measurement. Any questions about this? Okay. So a little bit more interesting is what's called an inscribed angle. So again, I'm going to just draw a circle. And so an inscribed angle doesn't have its point at the center, but its point is actually on the circle. So it's formed by two chords of the circle that meet at a point. Okay, so it's formed by two chords of a circle that meet at a point. And it turns out here that if this angle is theta here, then the measure of the angle for an inscribed angle is actually 1/2 the arc measure of the angle that it cuts out. So in that case, the arc measure of the arc would be 2 theta if the angle is theta. So if this angle was, 20 degrees, that would mean that the arc that it cuts out is 40 degrees. Okay? So any two, so if I have an inscribed angle, which is formed on the circle instead of at the center of the circle, then its measure is 1/2 the arc measure of the arc. And one thing, a nice consequence of this is that if you have any two inscribed angles, that should say inscribed angles that cut out the same arc, then they have to be equal. So if I draw something like this angle, let me draw it in a different color. If I draw this angle here, right, which is the same arc, then this angle measurement has to be theta also. Right? If I have any two different inscribed angles that cut out the same arc, then automatically they both have to have, measure 1/2 the measure of the arc that they cut out. So in this case, these two angles are going to be equal to each other. Questions? Okay. All right. So so let's just do an example of a particularly interesting example of this. Let's say that we have a semicircle, an angle inscribed in a semicircle. So what I'm gonna do is I'm just gonna draw this circle, and I'm gonna draw a radius here that goes through the center. And now I'm gonna draw an angle inscribed in the semicircle like this. So if I do this, and then this, right? So if I draw this red angle, then this arc that's measured out here, this arc is green. So this arc over here measures, well, it's half the circle, right? So it measures 180 degrees. And that means, well, what do we know? This is an inscribed angle. Its measure is always half the measure of the corresponding arc. So that means that this angle over here is going to have to be 90 degrees. Or in other words, a right angle, right? So the upshot is that every angle inscribed in a semicircle is a right angle. Right? So if I draw a whole bunch of different, angles here, maybe I'll draw them all in red. So if I draw this one, or if I draw this one, or if I draw this one, or whatever angle I draw, they're all going to be right angles, no matter what. So every single one here is a right angle. Okay, because as long as the two ends are on opposite ends of a diameter, so that they're inscribed in a semicircle, then we know that they all have to have measure 1/2 the arc measure. And if the arc measure is 180 degrees, that means the angle measure is going to be 90 degrees. Okay. Okay, any questions about this?
Yeah.
Yep.
Is that a difference between the diameter and the semi-diameter? And what's the formula for semi-circle?
Well, for semicircle, what? So for semicircle area is going to be 1/2 the area of the circle. So it's just going to be 1/2 pi r squared.
Okay.
for a diameter and radius, it's the same as for a circle, right? I'm even drawing the entire circle, even though all the action is going on in this semicircle, because in order to really see that these things are right angles, you need the other part of the circle, because that's going to be the arc that's cut out, and that's what you're really measuring as 180 degrees. But yeah, so the area of a semicircle is 1/2 that of the circle, and the circumference is also going to be 1/2. So the circumference of the semicircle is just going to be pi r instead of 2 pi r. And other than that, the formulas are the same.
So the diameter is circumference over pi, right?
The radius is the circumference over pi for a semicircle. And Dahlmann, yes, it means it measures exactly 90 degrees. So
Okay.
exactly. So let me write that down. So just because the diagram got a little cluttered, so it's exactly 90 degrees. Okay. Right. So the angle is 90 degrees and the arc is 180 degrees, because remember, the measure of the angle is always 1/2 the measure of the arc. Now, I didn't prove that to you. I mean, that's a statement that you have to prove. That's not an obvious statement, and we won't have time to prove it today. And I may not prove it at all, but just it's good to at least know that this is a statement that requires a proof, right? This is not just an easy statement to just look at and say, of course, it's 1/2 the measure of the arc. This is something that you need to prove.
But it is true.
It's true, yes, but and I'm telling you that it's true, but I haven't really explained to you why it's true.
Yeah.
Yeah, so I haven't really explained to you why it's true.
Okay.
Okay, but maybe I will, not today, but maybe some other session.
All right, Chief. Thank
Okay.
you.
Okay. So that's an angle example. Another example is these angles inside circles that are formed by crossing lines. So let's say you have a circle like this, and you have two chords that cross in a circle. Not necessarily at the center. These are not diameters. They're just two chords. And let's say I want to know what this angle is. So this is my angle theta. Well, what I have to do is I have to look at my two arc lengths over here. So this is going to be arc measure. So arc measure, we'll call it theta 1. And this over here, I have to look at the opposite arc. So the one cut out by, it says the vertical angle, which means the angle on the other side of this, which, by the way, also has measure theta, is the vertical angles theorem, that these two angles are equal. So this one here, I'm going to call arc measure theta 2. And then the formula is that it's the average. So the formula is that theta is equal to theta 1 plus theta 2 divided by 2. So it's the average of the two opposing arcs. Right? Exactly. So Gabriel, yes, that's exactly right. So it's the circle theorem states an angle in a semicircle contains 90 degrees. Right? So when you have angles made by two chords, you look at one arc and you look at the opposite arc. And then the angle is exactly the average of these two angles, right? So in this case, what do we have? So this tells us that, as an example here, if theta 1 is, say, equal to 30 degrees and theta 2 equals 50 degrees, then theta, the angle, would be 30 degrees plus 50 degrees divided by 2, or in other words, 40 degrees. Okay? So it's kind of, it's the average of what you get on one side and what you get on the other side. Okay? So these are kind of three different angles that we have inside a circle. We have a central angle formed at the center. We have an inscribed angle formed on the side, and then we have just an angle formed by any two chords, where you have to do this average. Okay? And if you think about it, I don't want to rush it, so maybe I'll talk about it next time, but the inscribed angle is kind of a special case of this, as this point moves toward the end of the circle. And what that means is that one of these arcs is going to end up going to 0. And so it's going to be the average of 0 in the other arc, which is half the other arc. But that's maybe too fast, and I don't want to rush that into today. So I'll talk about that next time, how kind of the formula for an inscribed angle is a special case of this formula for an angle inside the circle. Okay, it's kind of a limiting case of that formula. So I'll talk about that a little bit later. But applying this is straightforward. It's just the angle measure is just the average of the arc measures. Questions here? Okay, so one last example of angles inside a circle, which will be angles formed using a tangent line. So let's say that I have, again, a circle, and I have a chord inside the circle, and then I also have a tangent line to the circle. So remember, a tangent line is a line that hits the circle at exactly 1 point. Okay, so this is what's called a tangent line. So I have a chord circle, so I have a tangent line, and I have a chord of the circle. And now let's say that I want to measure this angle, theta, okay, between the chord and the tangent line. Well, it turns out that this theta, what is it? It's exactly half the arc measure over here. So this arc measure over here, if I labeled it, would be 2 theta from here to here. Okay, so if I want to know what's the measure of an angle formed by a chord and a tangent line, that's always half the arc measure of the arc that's cut out by them. That's cut out by the chord. Okay, so if the arc is 2 theta, then the angle is theta. And in particular, we have this other result, which maybe I'll draw right here. If I have a radius and a tangent line like this, well, the radius, remember, I can always extend it to a diameter if I want. And then this arc length over here is 180 degrees. That's the arc measure, because it's half the circle. And so what do we say? The angle between the tangent line and the radius is going to be 1/2 the arc measure. And the arc measure is 180 degrees. And so that means the angle is going to be 180 degrees times 1/2, or in other words, 90 degrees. So this is going to be a right angle. And so this is this theorem that if you take a radius and you take the tangent line and you look at the angle between them, it's always going to be a right angle. Clinton, do you have a question? You have your hand raised?
Yeah, the question I wanted to ask was regarding the first theorem there, the angle formed by the tangent to a circle and a chord.
Yeah.
Yeah. So the diagram, the angle starts inside of the circle, but then it goes to the tangent line, and the tangent line is outside of the circle. So are we considering the portion of the angle inside along with the portion of the angle outside that small portion?
Yes, it's the whole angle. So we're considering the whole angle because it's the angle formed by the chord and the tangent line. So the circle is there, but when you write the angle, you're ignoring the circle. It's just the part of the angle that goes from the chord to the tangent line. Yeah. So you're not considering the circle, you're going the whole way from the chord up to the tangent line. That's the angle that's being considered. Because you've got to form the angle with straight lines. So it doesn't even make sense to talk about the part of the angle inside the circle, right? Because depending on how big you draw it, more or less of the angle might be inside the circle. So you have to draw the angle between straight lines. So it's going to be the chord and the tangent line. And so yes, so some of that will be outside the circle, and that's okay.
Yeah.
Okay.
Sure.
Good. Other questions? Okay, so let me do one last example. This one is kind of tricky, but it's a fun example that we can do. And then I'll give you the homework. So I'm going to draw the following diagram, which involves two circles. So there's going to be a big circle and a small circle. And they're going to be tangent to each other. Let me just draw it like this. So we've got two circles here. Let's draw the circle a little better. Okay, so we've got these two circles, and I'm going to draw the following lines here. I'm going to draw a kind of complicated diagram like this. Okay, so let me label all of these points. So this is going to be A, B, C, D, E, F, and then this point in the middle is going to be G. And the question is, show that angle E is equal to angle F. Okay, so this so we have to show that angle E is equal to angle F. Okay, oh sorry, somebody is I need to just mute everybody.
Yeah.
Sorry, let me mute everyone.
Yeah, but can we change? Come back, sister,
okay,
please.
yeah, we'll be done. We'll be done in 10 minutes. Okay, so the question is show angle E is equal to angle F. And I'm not telling you the measures of any angles. We're not going to have any actual numbers. And well, the answer is, well, angle E, we know that angle E is an inscribed angle that cuts out the arc AB. But this angle, angle G over here, or angle AGB, is also an inscribed angle in the same circle that cuts out the same arc. So we know that these have to be equal. So angle E has to be equal to angle AGB. Right, I used 3 letters just to be clear that this is angle AGB. Because they cut out the same arc. They're both inscribed angles, so they both have to measure 1/2 the measure of this arc. Okay. So I'm just going to give little justifications. So this is inscribed angles with the same arc. Now, AGB is going to be equal to angle DGC, and that's because these are vertical angles, right? This here is angle AGB, and on the other side is angle DGC, and they're formed by the same lines. So they're going to be the same angle. So this is because they're so-called vertical angles. But then what about angle DGC? Well, this is an inscribed angle in this big circle that cuts out the arc from C to D. Here we have another angle in the big circle that also cuts out the arc from C to D, which is angle F, right? So in this case, we get that this is equal to angle F, and that's for the same reason as we had before. So inscribed, these are both inscribed angles with the same arc. And then this is what we wanted to prove, right? We wanted to prove that angle E was equal to angle F. If we were writing a formal proof, we would write out statements and reasons and columns and everything, but I want to just give you a quick reasoning that we can compare this angle here in one circle and this angle in another circle by using a combination of these inscribed angle theorems and the fact that vertical angles are equal to each other. Okay, Dalman, if nothing is showing on your screen, I think it must be something on your end because I think everything is working here. So this is kind of a cute proof that tells you that these two angles, you can show they're the same even though they're in different circles because you can go from one circle to the other using these vertical angles. Okay, so it's just a nice example. Again, we haven't really been emphasizing proof in this geometry unit. In the spring, if people want to do a geometry unit emphasizing proof, we can do that, or we can do another topic. So I'll send out a survey about that. But this is one kind of quick proof over here that you can show that these two angles have the same measure. Okay, so that's it for today. So for homework exercises, there's one. So the first one is just what's the circumference of a circle whose area is 8 pi? So actually these radius formulas that Theophilus was asking about should be useful. And then the second one involves a diagram. So I have to draw you the diagram. So give me a second. So in the figure below, let me draw the diagram. So there's going to be a circle. So here we have a circle. And we have a triangle inscribed in the circle here. So this is BCD. And I'm going to tell you that this angle here is 70 degrees. Okay, so this is B, this is C, and this is D. And then I'm going to draw a tangent line to the circle here. I'm going to draw a tangent line, and I'm going to tell you that this angle between the tangent line and line BC is 60 degrees. So in particular angle, and so I'll call just a point A here on this line. So in particular angle ABC is equal to 60 degrees. This is given. And so the question is to find angle CBD, right? So this is the angle theta that you want to find. Okay, so that's the question. And of course, I'll send this PDF to you on the chat so that you'll have access to the diagram when you do this.
Oh,
Okay.
yeah.
Yes, question, Clinton?
Oh, okay. I just wanted to comment.
Yeah.
So in the diagram there, angle CBD is theta.
Yes.
And,
Yes.
and then because angle DB, and there should be another letter on this side, right? To complete
No,
angle D.
I don't think we need any other letters, right? ABC, I have enough letters to define all the angles that matter here.
What if I want to define the angle that is equal to 70 degrees?
That's BCD. That's angle BCD.
No, I mean this 70 degrees is equal to the angle that between theta and this core.
It's like this angle here?
No, on this side.
This
B.
angle here. This angle here.
Yeah.
Okay, I see. Okay, so we call that E. Right.
Okay.
Okay, so if you wanted to do angle DBE, that's another angle.
Okay, so I just wanted to say that angle DBE is 70 as well. So angle theta will be 180 minus 60.
I don't think you can claim that, right? Because so why should angle DBE also be 70 degrees?
Because angle BCD and angle DBE has the same arc. They call the same arc.
BDE. Oh yes. Okay, so that's good. Okay, so don't give it away yet. Let's let everybody figure it out. Okay. So I think you know how to do it. But we'll discuss it next week. Okay.
All right.
Okay. So all right. So these are the homework exercises, and so next week we'll discuss circles in more depth. And let me just give you a little preview. So a little preview is that we'll have class on January 26th and on February 2nd. There's going to be no class on February 9th. And these here, on these two classes, we're going to finish the geometry unit. And then, of course, we'll have class on February 16th, and so on. And this will be a new unit. And I'll get input from the participants in terms of, what you'd like us to cover during this new unit. Okay. And so February, that this will go through, until May. Okay. Okay, great. So thank you everybody for coming. Thanks for your attention. And remember to put your name into the chat if you haven't done so already. If you have, you're recorded. And are there any questions or comments?
Yeah, thank you so much.
You're welcome, Sange. All right, anything else? Okay, in that case, I'm going to stop the recording here.